So this video is going to continue our discussion of surface plate equipment, and we're going to start to introduce other tools like 123 blocks and V blocks and how we can integrate them with our height gauges and drop gauges to do these surface plate inspections. So we're going to talk about 123 blocks, V blocks. We're going to discuss Joe blocks in depth. Joe blocks have applications throughout metrology, but particularly useful for working with surface plate techniques. So we're going to discuss them in detail. The sine bar and the angle blocks we're going to talk about in the angle discussion, measurement of angles video, but we're also going to integrate gauge pins, which we talked about in hole inspection, but they also have some applications in surface plate measurements. We've got some jacks that we're going to introduce, and we'll also talk about clamps, that precision tool clamps that you can use. So how we integrate those with the gauges we already covered in a previous video is what hopefully what we're going to know by the end of this series. So we're going to start off with 123 blocks. They're just used for fixturing parts. These blocks here have near perfect perpendicularity, parallelism, and thickness. So flatness, parallelism, perpendicularity, surface finish. So when those blocks are manufactured to such a tight tolerance, it kind of extends your surface plate and allows you to raise parts up or register parts at 90-degree angles. It pretty much lets you build any stable fixture that you need in order to fixture the rest of your setup, to set up the rest of your inspection. Sometimes these blocks have threaded holes, like this one, so you can actually bolt these together or bolt fixtures onto them. Other ones just have through holes. Either way, they're great for setting up and creating fixtures. The one thing I do like to point out is they're not guaranteed to actually be 1 inch by 2 inch by 3 inch. They actually are guaranteed to be parallel and flat, but size varies on these from the manufacturers. And size is really not important to setting up your part. But sometimes people have a tendency to use this as if it were a 1 inch Joe block or a 2 inch Joe block. And you really can't, because they are varying in size. That also means you can't mix up 1, 2, 3 blocks that aren't matched to each other, because they'll be matched to their size, but you start grabbing from different sets and using different blocks, they're no longer going to be matched. So we call a 1, 2, 3 block, anything. It could be a 2, 4, 6 block, which would be much larger, or a 1, 2, 4 block. Just kind of common terminology. When you say a 1, 2, 3 block, it could mean any size, but 1, 2, 3 is the most common size available. And because you can raise up your parts and treat them as if they're still on the surface plate, it really helps to fix your parts and make your surface plate inspections a lot easier. You can also use them as a registration gauge. So in this example, if you needed, for some reason, getting a direct measurement might be easier, but you can also treat them as parallel surfaces for when you need to grab, treat them as a reference surface that's just raised up above your part. I've done this a number of times. Sometimes I straddle a 1, 2, 3 block across the part and then register my tool off of the 1, 2, 3 block. But just remember, it's an option when you're working with these. Another kind of nice way to use them is to lift up maybe a shaft part like I have in the picture. And because you are lifting it up and using a matched set, you can now move the datum. If you can see in the drawing, datum B here is not on the end. In this example, datum B is off of this surface for whatever reason. There probably is some sort of mating face registration there for this part. So in this way you can lift up your part and then use your height gauge to get direct readings off of the top of the block to each ring on the part. So if, for example, it's going to be a little easier for me to work with the scribe, so I'm going to switch to the scribe. And I'm looking at 0.995 for that first step. So let's move everything so you can see it on the camera a little easier. All right, so I'm going to zero, just like we did in the last video. And move up. See if I get 0.995. And I am reading 0.956. And let's see, what should I be reading? I may have made a mistake in my setup, so I'm going to verify my zero. Yeah, my zero's good. Yeah, so I'm about 0.956 on that measurement. Let's see what our caliper says. Yep, so pretty far out of print. And then, you know, those steps I just went through, you get a drastically different reading. It's a good way to do it. Verify your zero, repeat the measurement, be a little bit more careful, make sure you didn't make a mistake, and then verify with a sanity check. So I did use the height gauge correctly. It just happens to be that part is far off from tolerance. I'll switch back to the presentation now. Oops. Oh, a little too far. So this is a great way to get a direct reading. I don't have to do any shop math by registering it off of the end and then subtracting my height gauge movement from the bottom, figuring out how long this is and doing the subtraction. You can also very quickly register the part, take a reading, and then rotate the part, take another reading, rotate, get all the way around the surface. That's something you should do no matter what, whether you're using a test indicator, scribe, or even a different gauge altogether. Remember to check your entire surface to make sure it's within print. Now, I've mentioned match sets, and this is going to take us into our V-block discussion. So match sets should be serialized with the same ID number. These 1, 2, 3 blocks don't get a serial number, but I did buy them at the same time. And you can verify that they are the same size by running an indicator across each one and verifying that you get the same reading on every surface. Same thing with these V blocks here. They have a 25 engraved. I'll show you that next time I switch the camera over. So they have a 25 on each of them. They came from lot 25 essentially, and they will be matched for same size. So essentially, when you have a match set, you can assume they are identical and interchangeable, and you can get match sets of 2, sometimes 3, but every once in a while 4, but most of the time the manufacturers just sell them in pairs or in triplets. They're going to be made at the same time by the manufacturer, ground at the same time, and come off of their grinding process with the same size. And it makes inspection much easier when you're using match blocks and you have larger parts that you need to use multiple blocks for. So this is going to lead us into our V-block discussion. So V-blocks are great for holding round parts. That's one of their main purposes, so that when you have a part that's round, you can stably hold it and rotate it around to do your entire inspections. Again, I have a match set here, so I can do two. If I only had one, I could still just register this on one V-block and do the same thing. But as it gets more out of balance, it's nice having a matched set because holding the balance is difficult. So this part was designed so that we could very easily balance it across two and practice our measurements. They come with clamps, so if you want to clamp down on it, you can slide this over. The V-block. There's grooves on the side of the V-block. There we go. And then you can just clamp down. So that it's balanced. So now there's force being applied straight down. It's being registered into the V-block so it can't move, and now it's fairly balanced this way. And again, I mentioned 1, 2, 3 blocks are near perfect, and so are V-blocks in terms of flatness and perpendicularity, parallelism, angularity, surface finish. You can pretty much assume in most cases that when you're using a 1, 2, 3 block or a V-block correctly, you're not introducing any additional error. There's maybe 1/10,000th of an error difference. You can check the manufacturer for those numbers. But in reality, compared to most tolerance zones, it's negligible for most applications. So, we'll go through a few examples using the V-block. This is a circularity cylindricity example where you just rest the part inside of the V-block and then rotate it around. When you are setting up your part on the V-block, it's going to be very important to make sure your indicator is centered on the top diameter. So when I go to measure these parts, I'll demonstrate that. But we talked about this in the last video also. If you're not sweeping and finding center, you're not going to be able to repeat your measurement, and you're not going to get all of the error in the measurement. So I'll show you how to sweep for center, and it's actually quite easy once you get the hang of it. So let's measure these parts for circularity and cylindricity. These are GD&T properties. Circularity means how round is something, or you could say how much out of round is something, however you want to think of it. So I've got my indicator at a relatively horizontal angle to minimize my cosine error. And when you watch the indicator, I'm going to give it a little bit of pressure I'm going to go near zero, and then I'm going to grab the V-block and sweep in and out. And when that indicator starts to go the other direction, that's the highest point on the part. So it's fairly obvious where it starts to change direction, right? And then you can pause it there, you can set your zero, and then you can double check that yes, you are right there at the top dead center. Well, if this were automotive. And now you can rotate your part very gently. Such a small part. And we're getting very little error. I'm only getting a few tenths error, which could just be me moving it. We'll try it with the flange next. So I've got a little flange part here, and we'll do the same thing. Bring it up, we'll do a circularity check or a cylindricity check, and I'm sweeping for the high point. There is the high point. I bring in a little more pressure, or you have the option to move it yourself. Either way, double check yourself and then rotate around. Now this is a situation where I've got a kind of an off balance flange and it's maybe wanting to tip off. So one nice thing I can do is I can bring up a 1, 2, 3 block for stability, and I don't have to worry so much about it being out of balance. Although you do have to worry about the 1, 2, 3 block pushing on the part the other way, which is what I appeared to be doing. Grab. But I often use a 1, 2, 3 block to stabilize my setup when I'm worried about my part falling off of the V block. There we go. And now we can rotate around. And you'll see it jump because it's falling in these through holes, but otherwise it's pretty stable from what I can see. And if you check out the secondary camera feed, you'll see that too. Now this is a circularity or a cylindricity check because our part is registered in the V block on this surface, and that's where my indicator is. So that makes it either a circularity or a cylindricity check. If you have your part registered on one surface and your indicator on a different surface, that becomes a runout check. So that's the difference. They're not the same symbol. One is comparing a surface relative to the V block, stability. So basically you're measuring how much form error the surface has. And the other check, which I'll demonstrate right now, is a runout check. And you would be checking the error between the two surfaces. Okay, so I'll find the 0 and rotate around gently. And now I'm doing a runout check because I have my part registered on the V block surface and I'm checking the other surface and I'm not getting very much error. So keep that in mind as you start using V blocks and checking for runout and circularity and cylindricity. So when you're working with match pairs, it gets a lot easier to do these checks. Now you have to be, as I said, you have to be careful. You're going to be registering on your datum. If you check out the print available on the Pragmatic Metrology website for this part, datum A is this matched diameter on either side. So I can register my part on both sides, and then I could either measure cylindricity of those datums, of datum A, or I could measure the runout of the other diameters to them. And so let's demonstrate that real quick with it balanced quite nicely. Careful not to do that. All right. When you're working with match pairs, I recommend you give it a little pressure so that if there's any sort of error in how you set it down, you can self-straighten them and apply that pressure. So I've got this on datum A right now of the print. I'm going to sweep. This time I'm going to move the height gauge. You can either move the height gauge or the part. It really makes no difference. Whatever is easier, whatever your preference is. There's my 0, and rotate around. Looks pretty good. Not a lot of form error on that side. Let's do a runout check to this larger diameter. Let's See how well they run out to each other. And I still need to sweep, find center. I got a little lucky and maybe just adjust it a tiny bit and rotate it around. And then once again, we've got very little run out. I'm going to flip this around and let us check the very small diameter at the end for another run out check, because once again I don't have this diameter registered in the V block. I have this diameter, so I'm checking the run out between them. And let me move the height gauge. Now this surface has got quite a lot of chatter. I'm going to do my best to get it on the high point. And rotate it around, and maybe 1,000th of run out error. Like I said, there's a lot of chatter that is affecting my measurement. But and once again, using a matched pair of V blocks makes this inspection very easy. So you could do run out, circularity, cylindricity. If you're not familiar with those terms, I'm planning to do a video dedicated on GD&T, but in the meantime, feel free to look up some online references or there's many references and textbooks available on GD&T and what these symbols mean. But, suffice to say, a circularity check would be just in one plane, in one two-dimensional ring. And a cylindricity check would be across an entire diameter. A run-out check compares two different diameters, and that would be in one plane for a single run-out, and that symbol with two arrows is called total run-out, and that would compare both cylinders, the entire surfaces. Now up there I have concentricity, and if you see this symbol, you should know that in the most recent revisions of GD&T standards, the concentricity symbol has been removed. And in many cases, it should be replaced by true position. And in some cases, a run-out check would be a better application of what is desired for the part. So you could replace concentricity with a run-out check. If you still have concentricity on your blueprints, just check what year the GD&T standard that your print is referencing, and you have to apply the definition for that year. I think it was 2018 that the revision went through. So you're going to see concentricity symbols quite a bit, and just know that in recent years, either a true position or a run-out check is more than sufficient for verifying a concentricity symbol. And then a straightness check. Straightness check is going to be fairly simple. It doesn't involve any rotations. You're literally just checking for the high point of your workpiece. So I'm going to do a straightness check on the top surface here. So all you have to do is find the high point, set your 0, and then move to another location and find the high point. It was about almost 1,000th of error. So that would be a straightness error. There's no, well, actually I should do this on the diameter that is on the V block. That would be a more realistic application of the straightness requirement. So now I've got top dead center 0 on this end, and if I go to this end, I've got about a 0.5 of straightness error. And no rotation required. Just kind of looking for if anything is bent. Now you probably should rotate it 90 degrees and check for a bend in the other planes. So I've got 0, and again I got a little about half, so that could be taper. Either way, that's a straightness error as well. But you don't have to rotate it while you're measuring it. You're just doing 2 points or 2 or 3 or however many points you want to do. Okay. You can also run out with a drop indicator. I want you guys to remember that. It looks pretty much the same. I won't set up on the second camera to save a little time, but set it up over here where you can see on the main camera. And it's pretty straightforward. You can just sweep the high point again, make sure you're on the highest point. I can visually see it from here. I'm on the high point, and spin it around, and you look for how much the indicator is moving, which is almost nothing right now. You can't even really see it up on the screen. So, but I am rotating the part, and you can do run out or circularity or cylindricity checks this way as well. So here's some examples. I've already clamped. I already showed you one clamped. You can also do a vertical clamp, so you can clamp onto your part in a vertical fashion. You can also raise up, the part as I have in the picture and clamp it, so if you need to get a little clearance beneath the part. So just keep that in mind. Clamps are extremely handy. You can also actually, when we get to the gauge pins, I'll show you an example of how we can clamp onto the pin and then slide a part onto the gauge pin and do a check. We'll get to that in a few minutes. We're going to switch gears a little bit to talk about Joe blocks. And this is really we've used Joe blocks in almost every video, but this is the only video where I'm going to really go in depth on Joe blocks, talk about their accuracy and their applications. So a Joe block is precision thickness ground to a very, very, very tight tolerance. This will probably be the most accurate gauge that you have in most applications. With maybe your surface plate, I should say, is probably even tighter, but your Joe blocks are very, very accurate. And you can stack them together through a ringing process. So if I take my 1-inch block, I can add a 0.95 block to it, and if I ring them properly, which I'll go over in a minute, I get something that's exactly 1.950. With the amount of error that's added in stacking is so negligible, you're not going to see it unless you did it absolutely wrong. So that's what's really nice about Joe blocks, is the ability to stack them with zero error. Well, near zero. Once again, I say they're near perfect for size, flatness, parallelism, and surface finish. The tolerances are very tight, so in an application you're not going to really see it, but the manufacturers still need a little tolerance for them to make something. And they're very hard. They're going to be very, like, 60 Rockwell or higher. I'm not sure exactly, but they're very hard and resist wear, so you can slide them, and generally speaking they won't wear very much. Some blocks actually used to come with a wear block, some sets, and you were supposed to use that wear block as your last block, and that would be the one that would take the brunt of the wear, but that's becoming less and less common as these sets get cheaper and cheaper, and you can just replace an individual block for a few dollars, maybe 10 or 12 bucks to replace a block, and so it's really, the wear block has become less common. But I've still seen them in some older sets. Speaking of sets, let me move my height gauge out of the way. So they're sold in sets, and typically it's an 81 piece set, and the reason it's 81 pieces is that's the smallest number of blocks that you can combine to get pretty much any size, from say 0.1 of an inch to 10 inches. There's enough blocks here to get you anywhere in that range. Some sets will have less. I think 31 or so is another common set. And that won't get you quite as many combinations, and usually they leave off the larger blocks down here. But your 81 piece set is broken up into these increments. You have one block that's 50 thousandths, that's your smallest block. And then you have 10 blocks that go from 0.1 to 0.1009. So those are your blocks with 10 thousandth increments. Those are the only ones that vary in size by 10 thousandths, by 1/10,000th of an inch. The next range is from 0.101 to 0.150, and each one of those moves in 0.001 increments. So you have 50 blocks basically, starting at 0.101 and ending at 0.150. From there, the increments get larger. You have 0.2 to 1 inch in 50 thousandth increments. So you'll get 0.2, 0.250, 0.3, 0.35, 0.4, 0.45, 0.5, all the way up to 2 inches. And then from 2 inches you go, all the way up to 1 inch. And then from 1 inch you go to 2 to 3 to 4. So the only tricky part is, you need to figure out which blocks add together to form whatever stack height you're looking for. So some applications for stacking up blocks might be a sine bar, which we talk about in the angle inspection videos. Another application would be a transfer measurement, where maybe you want to measure how high this block is relative to the nominal stack of Joe blocks, and I'll demonstrate that later. So you'll build up a stack of Joe blocks, and then you'll do a comparison with a test indicator and see how much difference there is. So as I was showing you, there is the breakdown of the blocks in all the increments. $81 pieces. And when we talk about stack height, there's a little bit of a mathematical formula that should always include blocks that are in the set. Sometimes what people do is they look at a number like 1.3448 and they end up trying to pick blocks that don't exist to build their stack height, and they can't figure out how to use the blocks that do exist. So there's a method to figuring it out, and it basically works by starting off with the rightmost digit. Our rightmost digit is 8/10,000ths. There's only one block in the set that has an 8/10,000ths. So I'm going to grab the 0.1008. And when I subtract those two numbers, 1.3348 minus 0.1008, I end up with 1.234. So then I ask myself, what ends in 34? I could either ask myself what ends in 4. What ends in 4 is 0.104. That's my only one. But I can skip a step and say what ends in 34, because I know I have a 0.134 block. So what ends in, so now I have my 0.108 and my 0.134 block. And I do the subtraction, and now I need to get to 1.1. So I know I have a 0.1 in there. And then the last block I need is 1 inch. So my stack height typically is going to be 1 inch. Then I'll add my next largest one is the 0.134. I'll add my next largest one, which is the 0.108. Sorry, 0.1008. And then my smallest one, which is the 0.1. Really doesn't matter what order you do it in. I just like to do it in size order. And I'm going to show you how to ring these together in a minute. But these 4 blocks form up 1.3348. And you should use a micrometer to verify your stack height. I don't have a micrometer larger than 1 inch right now, so we'll do another example later. But we want to go through another few examples. So example 2.865, how are you going to get to that stack height? We don't have anything that ends in a 65, if you look at your increments, you have 0.101 to 0.150, but you don't have a 65. So you're going to have to use something else to get to the 65. And for me, I say, well, let's use the 135. So now I'm at 2.730 when I subtract those. All right. So 2.865 minus 0.135 Joe block height, 2.730. I'm going to, my next Joe block, what ends in 730? Well, 130 ends, I can get rid of the 30 that way. So now I'm at 2.6. From 2.6, I know I can use the 0.6 and the 2. So my overall stack height becomes 2, 0.6, 0.135, and 0.130, which are all right here in the middle of their subtractions, and then our last number. Another way to do it, 0.865 minus 115. I get 2.750. 2.750 minus 0.75 is 2. And all of these blocks are in the set. It fits, it does fit our increments. I can find all of those blocks right now. So here's the 2, the 750, and the 115. So these three will get you a stack height of 2.865. I could also use the 2, the 0.6, the 130, and the 135 to get the same stack height as well. So there's multiple ways to achieve the goal sometimes. Sometimes you won't choose the most efficient way. The first time I did 2.865, I did it the way on the top, and I realized, wait a minute, I made a mistake. I probably could have done this easier. And when we've talked about go no-go gauging in some other applications, there's some applications where you want to set up a go stack height and a no-go stack height, and you need to use the same blocks, right? Because your go and your no-go will be so different that the base blocks, the larger blocks, are the same. But you can get around that if you're a little creative. To get a 2.865 go, we could use a 2, a 0.7, a 0.150, and a 0.5. Sorry, and a 0.05, as shown here. That will get me to 2.865. And to get me to 2.870 no-go, I could use a 1, a 0.750, a 550, a 450, and a 120. 5 blocks, but again, I don't overlap any of my blocks if you're a little creative with how you do that. And you notice 0.550 and 450 add together is 1 inch, plus 1 inch is 2 inch, plus 0.75 is 2.750, and then you're adding the 120 at the end. So that's how I kind of approached it. I knew I could get to 2.75 pretty easily by splitting up the 1 inch into these two pieces, and then I just needed my last piece here. So keep practicing. If you're having trouble with the math, remember, look at the right side of the number and work your way using the blocks that you have. And then when you start seeing you could have combined some blocks, just remember that for next time. So I've talked about the how to assemble these. Let's do it with a couple of blocks that are beefy. So basically, the first thing you're going to do is you're going to cross them together. And actually, the first thing I would say is wipe them off with your fingers. Grab any oil or dirt or dust and just give them a nice wipe down. And then cross them and twist them. And then slide, and now you're ready to go, right? Just the force of vacuum is holding these together. So I'm going to do that again. Okay, so I'm going to cross them, I'm going to twist them, I'm going to slide them, and now they're being held. Can't pull them apart easily. Okay. It's pretty powerful suction vacuum force when you do it right. So I could add another block, twist, slide. I can add another block, twist, slide, and you can just keep building it out that way. Now sometimes these larger blocks get a little unruly and they get a little more tricky, but you can still do the same basic premise. You might have to slide a little bit more and be very careful about the gravity, the weight of these blocks, but otherwise you still end up with a 7-inch stack in this case. So just be careful. The lighter blocks will be held together by vacuum force, but the larger blocks won't be. So and just follow this 4-step process every time. And you'll want to verify with a micrometer. So before I switch the camera, I should have verified. So I have the 130 and the 135. So I should get, what, 265 if I did my math right? And oops. Let's take a look at that. I need to focus my block. There we go. 265, maybe a tenth of error, but actually this micrometer is about a tenth out of cal off zero. So actually got it together just right. So you don't have to verify with your micrometer every time, but it is a nice habit when you double check yourself that you grab the right blocks. On a number of occasions I've caught a mistake where the person building the Joe block stack grabbed the wrong block, made their stack, used it to check their part, and then when I do the same thing with my own blocks and my own stacking, it was not passing. And the machinist in question even said, here, like, do you want to use my blocks? I stacked them up for you. I was like, no, it's all right. I'll use my own. And it's a good thing I did, because he grabbed a block that was like 10 thousandths too small. And so at any rate, his part was wrong, and I was able to catch it before he made another one. And that's just because he grabbed the wrong block. If he had verified it, even with a caliper, not the most accurate way to do it, but it's going to find a 10,000th problem. So try to get in that habit when you first start off. But when you are very confident, I don't verify these when I'm certain about the blocks that I grabbed, because I do have a lot of confidence in them. So we haven't really talked about the accuracy of these yet, other than, I say they're near perfect. Well, what does that look like? With your grade B or grade A, also known as class 3, you're going to be maximum error on the small side is 4 millionths of an inch. And on the large side, 8 millionths of an inch. So practically nothing, right? For your A plus, your double A, your triple A gets minus 1 millionth of an inch or plus 1 millionth of an inch. That is just very, very accurate. And that contributes, that surface finish and that level of accuracy contributes to that vacuum force that's holding them together. Now, I do want to point out, I don't have one of these here to show you, but there are round Joe blocks, as well as Joe block holders that can hold, a very complicated stack together. You can clamp these down in a clamp like this. They come in varying sizes based on the size of the blocks you're going to be stacking. And then you have round ones that will help you get into radiuses and diameters and help you check those. Internal grooves I've used. When you have like a ring groove and you want to check how wide is the groove, sometimes I'll use round blocks on both sides. And Those round blocks I've seen in 0.2 size or 0.4 size. There's a few sizes available, not nearly as many as a 81 piece set, but pretty handy. If you end up measuring a lot of parts that have those features, or you have complicated stacks that you're using as a hand go no go inside of a part, you're not using it on the surface plate. Invest in a clamp and maybe invest in a round block as well. So next up, we haven't talked too much about how to use these in a height gauge situation, but it is a great tool. Let me put away all my blocks so I can find them when I need them. It is a great tool for doing a height measurement with an indicator, because when you isolate the indicator movement and the height gauge movement, you end up using just the accuracy of the gauge, which the Joe block, which we said is right minus 4 millionths of an inch or plus 8 millionths of an inch. Very, very accurate, more accurate than anything else we're using. So in that way, you kind of minimize the error. So this is you see in the pictures on the right side, I'm zeroing, actually on both sides, both pictures, I'm zeroing on the Joe block height, and then I'm going to compare it to the part height, and you'll see, yeah, the part height indicator read 0.001 lower than the Joe block stack. And you don't have to move the height gauge. You're just using the difference between the indicator and the Joe block stack, and you get a very precise reading that way. So let's demonstrate that. So first of all, since I don't have a drawing for this part, I'm going to build up a stack that will allow us to verify with a height gauge. So 513, so I'll grab a 114 and a 0.4. Now 0.4 happens to be one of those Joe blocks that looks symmetric. And so I get in the habit of, okay, it's definitely not that size, 0.4. So I'm going to do it there. I'm going to cross them.